In this video, we're going to look at how we can use linearity, or what's often called differentials for some reason in this particular application, to estimate error bounds for a function. For local linearity of a two-variable function, a reminder that we have this simple formula that the difference in the f values can be predicted by looking at the change in x and the change in y and multiplying each of them by their respective partial derivatives. What we then think of when we're talking about error analysis is that we measure the x value with some number, but the real x value might be somewhere different. And so this delta x represents the error in the term that we've measured. And we might have an error measurement in the y direction, and we're interested in how far off our computed function value would be given those two errors. So these would be input errors, and then this would be the output error. In the way things are often represented in scientific literature, we would often have a measured value plus or minus some error. The idea is we don't know what the error is. We just know that we might be off by plus or minus 1 centimeter if we're measuring long distances, or plus or minus 1 degree Celsius if we're reading a thermometer. When we represent this, we're going to be replacing or thinking of that error that we have in absolute values, so we don't have to worry about the direction or the sign of the error. And once we've had that positive quantity, we're going to imagine that there's some maximum error. That would be that, plus or minus 1 centimeter. The actual error might be half a centimeter, a quarter, whatever. We're worried about the worst case scenario, so we're going to focus our attention on the max error because that's actually what's listed in these kinds of measurement plus or minus statements. We then want to compute the maximum positive error in the function output. So we want to know how big this error can get in the worst possible scenario for the errors in x and y. And we basically take this formula here and replace the possible error that's exact with the largest possible error. And the way we handle the signs on the other two terms are we basically put absolute values around both expressions just to make sure everything is additive. We never have cancellations of the errors. And otherwise it's the same. We take the maximum delta x possible, but otherwise it's the same formula we started with, and the same thing for the possible error in y. This is the worst possible error bound we can get, and it's based on the worst possible errors in the two input functions. If we go to 3 variables, we would use 3 terms like this. Now this makes a lot more sense if we look at an example, so let's do that next. All right, let's imagine we have a cylinder, and we've measured some properties of that cylinder. In particular, we've measured the radius as 2.5 centimeters. We've measured the height as 15.0 centimeters, and the mass as 330 grams. First of all, from that we should be able to calculate the density of the cylinder, and that's totally reasonable. The density is going to equal the mass over the volume. And the mass is already given to us, that's 330, and the volume is going to be pi times r squared times h. That's the volume of a cylinder. And if we put in the values we were told, we measured 2.5 for the radius, we measured 15 for the height, and we compute, and we get a density of 1.018 grams per cubic centimeter, approximately, because we just rounded and cut off that decimal. All right, that's not too bad. It's a very straightforward calculation. We measure these properties, and we compute a derived property, here the density of that cylinder. However, we know that there's going to be error in those measurements. In particular, we might be off in our measurement of the dimensions. If we're doing this with a ruler, there's going to be some error in that. And if we have a scale, it might be off by a certain amount as well. And notice again this terminology or this notation of a plus or minus error for both of those quantities. These represent the max error in both the radius and the height. And this property here, this plus or minus 2 grams, is the max error in the mass. All right. So how do we use these to compute the error bound on the density? So we think the density is 1.018 grams per cubic centimeter. Perfect. But is it really 1.1? Or could it be as bad as 1.5? Well, we don't know until we figure out the impact of these measurement errors on our calculation. So our goal is to be able to say that our density is equal to 1.018 plus or minus some other quantity. And that would be our error bound for the density. Well, how do we get to that? What we're going to be using is our linear approximation. But to get to our linear approximation, we have to have our formula for our density, and we're going to need the derivatives of that with respect to m, r, and h. So we notice that this is a function of mass, radius, and the height. Well, that means our density error, the bound on that error, is going to be equal to the derivative of the density with respect to mass times the max mass error plus the derivative of density with respect to, let's do radius next, times the maximum radius error. And again, the absolute values are here simply to eliminate plus and minus errors canceling out. Last but not least, the height times the maximum height error. So this is how we reflect the linearization formula for errors or extend it to errors in a particular application. And this error bound is what's going to go in here when we're done. All right, let's compute some derivatives. The derivative of density with respect to mass is nice and easy. The other two are constants. So we end up with 1 over pi squared, pi r squared times h, and the mass derivative is just 1. The derivative with respect to radius was our next term. Now here, this is like r to the minus 2. So we'll have m over pi and h. Then we'll have negative 2 r to the negative 3. And last but not least with h, we would have all of these other terms as constants, mass over pi r squared, and the h is to the power negative 1. Its derivative will be negative 1 h to the negative 2. We then evaluate that at, what were the values we had? We had 2.5, 15, and mass is our first one, 330 grams. So we evaluate each of those at the measured values. Those are our best guesses for all of these terms. H equals 15. And we get, through some calculator work, 1 over pi times 2.5 squared times 15. And that's approximately 0.00395. Repeat for the radius. We get 330 over pi times 15. And this is negative 2 over radius cubed, 2.5 all cubed. And that's approximately equal to negative 0.8149. And then the height rate of change, mass over pi r squared. Mass is 330 over pi times the radius 2.5 squared. 1 over h squared when we're done that. And that is approximately negative 0.0679. All right. We're basically there. Pause. Okay. We're basically there. Take that last minute. The last ingredient is to put each of these values into the corresponding location in this formula, multiply by the plus or minus values that we had from the last page. Let's go back one step here. Mass was off by at most 2 grams. So this was 2. And the maximum radius error was 0.1 centimeters. The maximum height error was 0.1 centimeters. So we take this times 2, this times 0.1, this times 0.1 again. And if we do all those calculations, we end up with a lovely value of 0.096. And then the units there would be grams per centimeter cubed. And so what we can infer from all this is that we actually have a very good density approximation. We have a value here, and at most it's off by about 0.1. So this could go up to 1.1, down to 0.9-ish. Here's the exact value that we can include as a bound on our errors, regardless of which way the actual errors worked out. That's the key thing for this argument. This could have been up or down 2 centimeters, we don't know. At the end of the day, all of those effects together, if they all ganged up, would make a deviation or an error in our density estimate of this scale. And so this is a robust estimate of how far off we could be in our simple computed value. The key thing again, though, is all of this is based on the linearization formula, taking that and generalizing it to errors through the absolute values to take into account that we could have positive or negative errors. And we want to get the total or worst case scenario. Now with all of this calculation, there's a formula that often gets used in chemistry and physics that is related to this. And here what we want to do is explore how this comes from the calculus linearization idea. To get there, though, we have to remember the difference between relative error and absolute error. If we talk about an error as delta A, and we scale it by the value itself, A, so this is the error on top divided by the measurement, then that ratio is what we call the relative error. If we're off by 1 centimeter in 10,000 meters, that's a small relative error, versus off by 1 centimeter in a 2 centimeter measurement, that would be a very large relative error. Sometimes we talk about percentage error if we take that ratio and multiply it by 100. All right, so what's the formula that comes out? If we can write our function as a combination of simple powers, x to some power, y to some power, and z to some power, and that covers a bunch of cases, we could actually have, pretty similar to our last example, we could have x over y squared times z. Well, that is very similar to the cylinder example we just looked at. If we have that kind of formula, then we can look at or compute the maximum relative error in our output as simply being the relative error of the 3 variables coming in times the powers that go with them. All right, let's see how that works out in practice here. If our function is a simple combination of powers, it's easy to take the derivatives. We simply bring the power down front and only do that for the variable that we're differentiating. And we do that separately for each variable. For the next variable, it is just y that we're differentiating, so the x stays the same. And we only bring the power down for the y and subtract 1 from the power. Keep z the same. And then we take the z derivative, the x and the y stay the same, and we get 1 lower power for the z. What that gives us then is that from our error formula, the maximum error in f is going to be given by, or bounded by, the derivative here, that's fx times delta x, plus the fy times delta y, plus the fz times delta z. And what that gives us is an opportunity to try to turn this into this. To accomplish that, we're going to need to actually sub in our fx values here, though. We're going to have our x derivative, mx to the m minus 1, y to the n, let's make that a bit clearer here, and z to the p, times delta x, plus, I'm leaving a little bit of space deliberately here, we'll see why in a second, n times y to the n minus 1, z to the p, delta y, and x to the m, y to the n. This feels very abstract, but we're getting there. P minus 1 delta z. And we do all of that with the intent of then dividing through by f. Why do we want to do that? Well, we have to have that to talk about relative error on the left-hand side. And what that means is we're going to divide each of these through by f as well. We can't just do it to one side, we have to do it to both. But if we do that, what we end up dividing through by is, what's f? F is x to the m, y to the n, and z to the p. And notice what happens to most of these terms. The z's cancel, the y's cancel, almost all of the x's cancel, but we still have an m. So what do we get here for this one term? We have an m, we have a delta x, and if we look at the powers of x, there's one higher power of x in the denominator. Ta-da! We end up with relative error in x. And if we look at the same thing happening to all three terms, x to the m, y to the n, z to the p, x to the m, y to the n, z to the p. Again, this is dividing through by f for all three terms. We're going to have the x's cancel, the z's cancel, there's an n left over, there is a delta y left over, and we end up with one higher power of y in the denominator. And last but not least, we end up with p and a z, a delta z on top, and a z on the bottom through exactly the same parallel form here. So all of this calculus work leads to a nice simple expression for the relative error of x, y, and z being scaled by the power that goes with them. If we add those three terms together, we get the relative error in some function that we're trying to compute if it's a simple combination of powers of x, y, and z. Again, that's a formula you'll often see in physics and chemistry texts.